Hello, and welcome to our presentation on quantum computing for the time-varying linear quadratic regulator. My name is Casimir Dikasadis, and I'm with Marist University in Poughkeepsie, New York, where I'm the Director of Cybersecurity Education. My co-authors, Malik Nadali from Marist and Augusto Gonzalez Bonorino from Claremont Graduate University, are very pleased you could join us for this presentation at ICEQT 2026. Following a brief introduction, I'm going to introduce the time-varying LQR problem. We'll talk a little bit about the mathematics behind the transformation of variables that we are using, present our experimental results using the quantum computer, and finally offer a brief summary with some conclusions. Since there's a lot of mathematics in this presentation, I'm going to have to skip over some of the detailed derivations in the interest of time, but I'll refer you to our full paper in the conference proceedings and to the references in that paper, which I will be citing throughout today's talk. Now, to begin with, the linear quadratic regulator problem is well known in optimal control theory, and it covers a wide range of applications in which dynamics are linear and the cost functions are quadratic. There's many applications in mathematics, biomedical systems, management and business and economic systems, electronic circuit theory, social science, robotics, and many others as well. This is a broad problem that has been studied for many years using classical computing techniques. For this paper, we consider the finite horizon, time-varying, continuous time linear quadratic regulator. In particular, we're going to investigate using quantum computing algorithms to generate approximate values of the control function. We believe this can achieve a significant speed up in execution time. Our approach to make this algorithm suitable for a quantum computer involves a change of variables, which turns the matrix Riccatti equation into a second-order linear differential equation with non-constant coefficients. We can then solve the matrix equivalent of this set using an enhanced hybrid version of the Harrow-Hassum-Lloyd or HHL quantum algorithm. To begin with, let's introduce the time-varying LQR, the Riccatti equation. As shown on this slide, we are attempting to minimize a cost function over a time interval as shown here, where we have an initial and final time interval subject to constraints on the problem. There is a constant in front of the integral, which for our purposes we'll assume to be 0 through the remainder of this calculation. This is a fairly standard format for the Riccatti equation, and several of the variables are defined on the slide. I'm sure you can read those for yourselves. Now let's consider a slight restructuring of this, the matrix Riccatti equation, which is given by the formula shown in equation 5 on this slide. It's known from prior art that if the function coefficients b of t and a of t are both invertible functions, then the matrix equation, that's equation 5, can be transformed into a second-order matrix linear differential equation as given by equation 6, using the change of variables listed on this slide, where we've introduced a new variable v of t, which is an invertible time function. This has been proven in prior literature, and I won't repeat the proof here. Now, the LQR problem requires us to solve a version of the matrix Riccatti equation given initial values in a time interval, as shown here. We're going to make a simplifying assumption that the function r of t and the function a of t are both given by an n by n identity matrix in order to simplify the format just a little bit. Then, using results of the theorem on the prior slide, we are going to make a change of variables as described here. After some manipulation described in our paper, this reduces to the form of a second-order linear differential equation with non-constant coefficients, as shown here, where we've introduced a constant diagonal matrix S into the proceedings. Now, there's some details in our paper as to exactly how we've derived this result. The point is that we are transforming the Riccatti equation into a form that is more easily manipulated by the HHL algorithm on a quantum computer. In order to more fully utilize HHL algorithms, we introduce the following W function notation as given here. And we obtain a series of transformations for V and W and for the first derivative of V. Substituting a variable for convenience here, the function matrix x of t, we can rewrite this in matrix notation. That's significant because in quantum computing, most of our calculations are traditionally done using matrix vector or tensor multiplications. One way to find the solution of this system of equations involves setting an initial condition and then calculating the following series of vectors as shown here. We can perform these computations and generate eigenvalues and eigenvectors for the resulting matrix set, as well as a passage matrix for this solution. Again, in the interest of time, I'll need to skim over the derivation of all of this. Details are provided in our paper. So we've reached the point where we can say that solving the Riccatti equation in matrix form is equivalent to finding the solution of the following matrix equations. We can now use the enhanced hybrid HHL algorithm to solve the system of equations shown on this slide. We note that the H matrix is sparse. It also happens to be Hermitian for all the cases that we're dealing with here. It turns out that the HHL algorithm can be used to take problems with exponential time execution, and in some cases, such as this one, reduce them to polynomial or better time execution, resulting in significant time savings. The quantum circuit that we're using for the HHL algorithm is illustrated on the top of this slide. This is a standard HHL algorithm that you will find in many quantum textbooks. It involves using a building block called the quantum phase estimator, or QPE. That building block is shown in detail on the lower portion of the slide. The quantum phase estimator estimates the phase of an eigenvalue of some unitary operator U that we've created using the properties of Hermitian matrices. The quantum circuit shown on the top will perform quantum phase estimation. It will also allow us to solve the system of linear matrix equations that we introduced earlier. And finally, through measurements, we can get a result in classical terms. We're using the linalg package from ICEQT, the quantum computing language, so that we can essentially treat the HHL algorithm as a black box for purposes of these computations. Now, to test the performance of quantum algorithms versus classical algorithms, we're going to solve a sample problem using both techniques and compare the results. Once again, we have the expression for the optimal control problem written out in differential and matrix equation form as shown here. Our goal is to solve this system of equations and find the control function that minimizes our cost function. We've simulated this using both quantum computing algorithms and classical computing approaches. Now, once again, we are solving a system of equations with the sparse Hermitian matrix H as shown in the top part of this slide. The classical solution yields a control signal which is related to the state of the system. We also have something called the full state feedback gain matrix given by K of t in this case. We're going to graph K of t in just a moment on the next slide and compare the results from a classical solution and a quantum solution. We've specifically chosen this as an example problem because it has a closed form solution in the classical case that allows us to do a proper comparison between the classical and quantum solutions. This graph shows our experimental results. You'll notice in both cases, when we compare the classical and the quantum approaches, they converge over time to the same solution. The error between our quantum solution using the HHL algorithm and a classical solution technique is extremely small to negligible. Now that's good news because it means we can use the quantum solution and take full advantage of the execution time speed up that's offered by quantum computing without sacrificing accuracy. You can see the convergence in terms of time cycles illustrated on the upper and lower graph for the different gain coefficients in our matrix. In conclusion, we've investigated the use of quantum computing, specifically the modified HHL algorithm, to solve versions of the time-varying linear quadratic regulator problem. We've shown that you can take a matrix Riccatti equation and using a change of variable transform it into a second-order matrix linear differential equation with non-constant coefficients. This is something that we can more readily solve on a quantum computer. We've done a sample case comparing the results of a known classical solution with our quantum approach to show that we get the same answer. There's negligible error between the classical and the quantum solutions. The quantum solution has the advantage of faster execution time and being more computationally efficient. In the future, we intend to expand on this work and to consider what happens if we try to address problems in linear quadratic regulators which are more complex and do not have as readily comparable solutions in the classical domain. Thanks very much for your attention, and we'll look forward to receiving any questions from you.